Good morning, everybody. Thanks so much for tuning in to the inaugural Where's the Moon contest seminar. Just to give you guys some background, this float was released in the Atlantic, and it's released for testing purposes. Seatrec is always trying to improve their technology and make a more durable float that will last longer. Just as a side note, the Seatrec float has an energy harvesting component to it, so it's actually generating positive energy in many parts of the world's ocean. So, hypothetically, these floats could last a very, very long time as they drift around in the ocean. But Yi had this idea to focus the community on trajectory prediction, because that would be very useful for scientists to kind of either predict or to potentially long-term to navigate where these Lagrangian drifters are going. And so Yi had this great idea that we could create a contest where we would all just kind of compete to identify where this float is going to go. And so we all got together and brainstormed a name for the float, and we came up with the monk. Because it's out in the middle of the ocean. It's very solitary, and it spends a lot of its time in rest and contemplation. But also it's an homage to Walter Monk, who was a great oceanographer and somebody who I personally really have a lot of respect for. Okay, so the agenda of this presentation. First, we're going to go over their introduction and format. Then we're going to do an overview of some common Lagrangian prediction frameworks and their error sources. And then, this is kind of the highlight of this presentation, we have two titans of the Lagrangian prediction world. We have José Manuel Echevarría, and we have Knut Døgestad. And they are going to present on their work, and then we're going to have questions and discussion. Okay, so first of all, I want to thank everybody for their participation. We are going to do this contest hopefully with some regularity, and we're going to continue to encourage participation with more prizes, increasingly compelling prizes for winners, and then we're hoping to have seminars to highlight these Lagrangian prediction techniques, and maybe focus some development and potentially even to develop a publication on best practices for this. So with that, we will get started. Okay, so really fun. So this is what I'm showing here is a plot of the first competition, and these are we received 24 applicants for the first competition, and these are the errors of every one of the predictions. And José Manuel Echevarría won with an error of 52 kilometers. There were only four entrants who had under 100 kilometers of error. And the question that I want to kind of tease apart is why is it so hard to do this Lagrangian prediction? It seems like if you put something out in the ocean and you waited a week, maybe you would have a better idea than 50 kilometers, or what? Maybe why does this distribution of uncertainty look like this? Okay, so we're going to go to kind of a common description of the problem. So we're going to say that we're going to start off, we're going to create an estimate of where the float is going to go. And so X is going to be our state vector. So this is, in this case, this is like where the float is. So X is where the float is. So this is like our GPS position. And then we are going to integrate that from some time to some future time step. And then we have some estimate of the ocean velocity. We're going to call that U hat. And if we integrate that from our current time step to our future time step, then we should have an estimate of where the future position is. So this U hat is going to be driven by an ocean model, or, you know, potentially, I mean, we're hoping that this is going to be a blue sky conversation. So there's a lot of exotic methods that we could employ here. We could have ensembles, we could have AI, we could have a lot of crazy stuff. But just for kind of the bread and butter Lagrangian prediction, we're just going to say that this is an ocean model. And so the ocean models that are commonly used, and I'm really interested to hear how these entrants have completed the problem, and maybe interested to hear from other people on this call of what they're doing. But I would say that the big ones that are commonly used are the Copernicus GLORIES product, which is a large-scale physical ocean model. There's the HICOM product, which is run by NOAA, which is a large-scale global model. And then potentially there's you could have some sort of regional ocean models using the ROMS system. So those are kind of, I would say, the three big pillars of the of ocean modeling for Lagrangian particles that I've seen. And so if we were to build on this, we say that error, which is that number that we were looking at before that that we're trying to optimize against, error is going to be equal to the true state of the true location of the float minus our estimate of the float. So then we can come up with our incremental error at every time step. And if we differentiate our error with respect to time, then we come up with an expression that looks like this, where we have this expression on the left, which is the gradient of the estimate of the velocity times the error, which is kind of the existing error that exists in the model, plus this kind of new model error that gets propagated into the system. So that's this estimate of the velocity minus the true velocity. And we're going to call this new model error, this term eta. So eta is going to be this basically how bad our we are at each additional time step, how bad our velocity field is. So and I want to mention that this is a linearization of the uncertainty, and so eta, then we can break it up into two different forms. We can break eta up into the model bias, and we can break it up into this eta prime, which we're going to call kind of everything that's left over from a fundamental bias. And the critically, you know, that what defines eta prime is that the expectation of eta prime is going to be 0. And so we're going to think of eta prime as high frequency things that are not resolved in a model time step. We're going to think of it as unresolved physics that are not resolved in by a model grid cell. We can also use eta to sort of be a catch-all term for interpolation or representation error in our integrating framework that in our Lagrangian prediction framework. So how we interpolate between velocity grid cells and then how we propagate that forward. So just to kind of put a point on this, on what eta prime is going to be, as far as like the different advection schemes that we can use that both interpolate the velocity field and then advect that forward. There's some really good ones out there. There's ocean parcels, which I use. There's OpenDrift, which Knut Dagestad is the lead developer of. There's Octopus. There's TrackMass, and all of these are. So this comes from a review paper by Van Sabeel et al. From 2018. This is one of the papers that I read in preparing for this talk. You know, all of these Lagrangian advection schemes or software packages, they're all pretty good. They use a variety of different applied math strategies, Runge-Kutta 4-5, Euler advection, Euler methods, and they, there are certain trade-offs with those, but they're generally they're pretty good, and they are freely and openly available, which is really cool that that these exist in the community. Okay, so to kind of explain a little bit why you would need to spend time developing these different advection schemes. This is an image that is it's kind of a conceptual image that describes that. So here in this top panel, we're going to say that this is a true ocean state. So you can see that there's a lot of really fine scale complexity here, and then each one of these paths that go through here indicate paths that are driven by different advection schemes. So if you have this really super fine scale complexity, you can interpolate that in a variety of different ways. You could do a very kind of crude interpolation of that, which might look like the field on the left, which would produce this kind of very steppy trajectory, this red line. You could potentially, so this would be, maybe you would just jump to an end member of the grid cell. This middle panel would be, maybe you could smooth it in some way, some kind of intelligent smoothing and interpolating, and maybe that would be this. So that would be kind of a smoother field. That would be this yellow line, and then maybe you could do a more advanced kind of interpolation, maybe like a spline interpolation or something, or you could change the time step of your integrator to be very fine scale time step, and that would be a different trajectory, like this green line. So this is kind of just a conceptual drawing of why the choices that you would make for your Lagrangian advection scheme potentially would influence your trajectory. This is a image from the Van Sabeel paper, and this is a review paper where they apply, kind of like they took that conceptual drawing in the previous slide, and they actually applied it into a real world case where they looked at several different where they compared advection schemes to theory. So these black lines are a theoretical solution to a specific type of grid. These vectors are the velocity field, and then it's kind of hard to see in this figure, but you'll have to trust me that there's like these red lines that are different from the black lines, and they indicate the difference between the red line and the black line indicates the uncertainty of the advection scheme. Okay, any questions about that? Any questions about that? There's some real experts in the advection scheme field on this call. So if I messed anything up there, please feel free to jump in. All right. So moving on. So going back to kind of that eta prime, that bias term and the eta prime term. So Lagrangian trajectories, they're nonlinear and they're path dependent. So that's, the error term from previous time steps propagates into the next time step, and then can potentially confound your results. So for these ocean models, the exact state of the mesoscale eddy field defines the path. We can't just rely on having, a lot of these models just rely on having kind of the right energy spectra in the mesoscale eddy field, but for our purposes, we really need to have everything kind of placed exactly right, or we're going to get the wrong answer. And so these errors compound over time. So this is the figure on the left is basically showing how you could get really different trajectories based on misplaced or uncertainty in the eddy field, and that would result in substantially different displacements at the future location. Okay, and then so finally, a final wrinkle of this is that the profiling floats they're doing exactly that. They're profiling up and down in the water column. And so they're experiencing ocean shear as they ascend and descend to park depth. And so and depending on their mission, they can spend a substantial amount of time at depth, and they can, a substantial percentage of their displacement can happen at depth. And so we really need to resolve not only the two-dimensional placement of the eddies, but we have to resolve the full three-dimensional field of the full ocean, which is difficult because you know many of the sampling sources that for data that we have are from space, they're remote sensing, and so it's difficult to see beneath the ocean and to resolve that full three-dimensional picture of the ocean and constrain that state to data. Which actually, I mean, which is a strong argument for really good profiling for floats that can give you lots of three-dimensional data about the ocean. Okay, and so finally, and I want to say, I want to just say, like, I don't know how AI is going to affect ocean modeling, but I do know how AI is improving my clip art, because all of these images were generated from OpenAI. Anyway, I love this one for sub-mesoscale processes. So so what we're showing here is on the left-hand side, this is like what a model, maybe a kind of a hypothetical model would show for ocean velocities. You know, it's very smooth. We don't have fine scale resolution. We you know, these models run on a global scale, and so in order we have finite processing power. We can't resolve things less than, well, the Copernicus model and the HiCom model both run at 1/12 of a degree. So that you know, that gives you an idea of it's several kilometers to tens of kilometers is the scale at which we can resolve processes. But of course, on the open ocean, if you go out on the open ocean, there's all kinds of complicated things that are happening at much much smaller scales than that. So, and all of these things affect float motion. So we can have surface gravity waves. We can have wind interaction. We can have internal waves. We can have currents, and many of these processes are not resolved in models, or if they are resolved in models, typically they're parameterized in the models, and the parameterizations may not be totally robust. So, so this is another source of uncertainty for these predictions. Okay, so going back to the math on this, we're going to have eta as a function of time plus our bias plus our eta prime. So our error is going to be we're going to call it our model error is going to be the integral of this eta term, and then we can look at the autocovariance of the velocity error, and that's going to be we're going to call that this c sub eta term, and then we can integrate that to look at the full model error covariance. This, I want to say that this was originally done by G.I. Taylor in 1922, and then it was kind of up to a contemporary derivation with a very similar thinking was done by Lacasse in 2008. So once you derive this term, then you can integrate it on short timescales, and if you do that math, then your error, your uncertainty, is proportional to time. So this is the so-called ballistic timescales for dispersive particles. This was a term coined by Taylor. And then on long timescales, the uncertainty is proportional to the square root of t. And so that is a term that was so this is the so-called dispersive timescales. And so this kind of gives you an inherent sense of, and then the final thing that I want to say is, if you do have model bias, so if there's this bias term, then you can see that if you integrate the, and you know, supposing that this is like a constant bias, we're making all kinds of simplifications and approximations in this derivation, because I really frankly don't have enough time to kind of I only have time to do the broad strokes, but if we assume that there's a constant bias, then if we do this integration, then there's going to be a bias term or a bias time scale that's going to be proportional to t as well. So kind of like breaking this down, answering the question of why are we why is it so hard to do this prediction? Why did we only have 4 entrants get under 100 kilometers of error? I think that the best way to think about that is that there's these scaling orders, there's these different scaling regimes, and there's these different scaling orders that happen. So initially, after we get our position and the float goes down into the water, we're in this ballistic scaling regime, where uncertainty scales by proportional to time. And then as we leave that regime, we go into a kind of a diffusive regime where it's the uncertainty scales according to the square root of time. And then if we do have bias in our model, which it's very likely that we do, then we transition over a long enough time scale. We transition to the model bias dominated uncertainty, and that is proportional to time again. And so over a week, that is why we're getting these uncertainties. So I'm actually really curious to hear the methods that people have used to achieve the results that they've gotten, and I think that it's hopefully going to encourage the community on these next competitions to maybe adopt them or refine them. And so just kind of I thought of doing a kind of a just back of the envelope, writing down different ideas that I have for improving predictions. So or methods that I'm aware of that people are using to improve predictions. So people are doing bespoke regional models, where they're doing potentially better or improved interpolation and advection schemes, potentially better representations of fine scale motion, or either through parameterizations or maybe AI, some kind of thing like that. Ensemble forecasts. That's actually what I have been doing most lately. Is spending time with an ensemble forecast, which seem to be, at least for me, fairly effective. And then the final thing is that we have a whole track's worth of data, and so you can the final idea is that you could potentially use your previous predictions to calibrate your uncertainties, or potentially use that information in an intelligent way. But enough about my ideas. I think that the reason why everybody has showed up is to actually hear from the people who did this successfully. And José, I'm so sorry. Anyways, I thought your last name was Rubio. I apologize. But anyway, so this should say José Echevarría, and so José is going to go first. José is soon. We're all rooting for him because he is about to defend his yes. dissertation. We know that he's going to be successful. So, anyways, José is a soon to be minted PhD from CICI MAR-IPN in Mexico. José is an oceanographer and geospatial scientist who bridges the gap between marine science and data engineering. His research leverages satellite imagery, machine learning, ocean transport modeling to track and understand pelagic sargassum dynamics in the Atlantic and Caribbean. Before transitioning to oceanography, José spent 5 years as an automation engineer designing embedded systems and data platforms, and he uses these skills to help him in his oceanography. So without further ado, I am going to let José take it away.
If anyone has questions, feel free to put them in the chat or the Q&A.
Okay. Thank you, Paul, for the introduction. Actually, Rubio is my second last name, so no problem.
Okay, all right.
Let me share the Can everyone see the presentation?
Yes.
Okay. Okay. Well, hello everyone, and welcome to this section of the webinar that I titled "Finding the Monk: How to Predict Where the Ocean Takes a Float." My name is José Manuel. I am a PhD candidate at CCMAR, as Paul said before, in La Paz, Baja California Sur, in Mexico. I won the first contest of I won the first contest of the Seatrec challenge, and my forecast landed like around 52 kilometers away from the actual surfacing position of the float. And today I'm going to walk you through the modeling. It makes this possible. To give you some background of where I come from, on my PhD research, I developed Lagrangian drift models. It's one of the objectives of my research. And here in this animation, you can see a simulation I built for tracking pelagic sargassum, the rafts detected by Sentinel-2 satellites as they drift through the Caribbean and the loop current. In this case, I use OpenDrift with the Copernicus marine currents, the Glory's 12 product. And when Seatrec announced the contest, I saw the LinkedIn post, and I asked if I can transfer what I do with the in situ drifter data with the 2D surface advection and adapt it to the 3D float that dives down to around 1,000 meters. And here is the challenge. Seatrec gave us the last confirmed GPS fix on June 2027. The task was to predict where it will surface nine days later on July 5, and it was located in the Gulf Stream. On the left panel, you can see the full 284 days previous history of the track of the float, and on the right is the official Seatrec portal where you can inspect the positions, the latitude, the longitude, the coordinates, and also the depth that the profile took on that specific coordinates. And later, the first step I did was to get the data for this prediction, for this forecast. And here we can see the product that I use is from the Copernicus Marine, the operational Mercator currents, specifically the global analysis and forecast. It has a spatial resolution of 112 degrees. It's around 9 kilometer spatial resolution. And I downloaded 8 depths to create a currents cube covering the entire duration of the mission, since the deployment of the float in the Gulf of Mexico to the final fixed position. I calculated the average depth of the profiles, and it was around 961 meters. And so I get the currents on the closest one was 902 meters. So it was close enough to simulate the advection in that the deepest layer. And I also tested adding the slope drift for the period that the float was on the surface, but as we can see later, I discarded this because the float, the waves didn't impact that much in the trajectory, because the float spent most of the time below the wave base. And here we can see the cube the 8 depth levels I built from the Copernicus marine product. And as I mentioned before, the closest layer to the main parking depth of the whole trajectory of the float, it was around 902 meters. So this is the layer of the. I will simulate the most of the time the trajectory of the float. And here we finally can make the monk. It's an infinite flow that is a patented technology that harvests energy from the ocean thermal gradient. And yeah, I got the trajectory, as I mentioned, since its deployment. It was more than 280 days. It's recorded more than 600 vertical profiles and covered more than 7,000 kilometers. The average transmission of the positions that I calculated was around. I modeled that it was around 11 hours cycle, and it spent 30 minutes at the surface transmitting the position and all the collected data. It got from the profile, the temperature, all the variables that it measured during the profiling of the water column, and it descends. I modeled the descent rate at 0.1 meters per second. So it's to get the whole column. It takes around 2.5 hours. Then it spent like 7.5 hours in the deepest layer, as I mentioned before, around 902 meters depth, and then resurface at the same ascent rate as the descent. To get this prediction right, you have to capture 6 main mechanisms: the mean currents, the mesoscale eddies, the meanders, the vertical shear, and the chaotic dynamics of the Gulf Stream. And in this here in this slide, we can see the modeling idea. As I mentioned, I calculate the mean depth of the parking of the float in the known trajectory, and it spent more than 98% of the time span below the surface. So if you hold a particle at one single depth, so the simplest approach maybe is take a single depth and simulate the drift. You will get the wrong predictions, because it's you have to take in consideration all this profile that it does, and that's what I built this 3-phase dive model: the 30 minutes in the surface, the descent, the parking drift at the deepest layer, and then the ascent rates. And here we can see the two Lagrangian frameworks that also Paul mentioned before, that I also use for my research with the pelagic sargassum. And I compare, here we can see the OpenDrift and ocean parcels. With OpenDrift, for example, I could write a custom Python particle class that computes its own depth dynamically at every time a step. So I can model this the particle in each depth level and do the interpolations of the current fields. And I also compare, like, setting a baseline holding particles at around 763 meters depth, and I use like this for a baseline to compare all the different tuning that I did on the modeling. And the key lesson here I took that it was that what it matters most is this vertical dive cycle. So you have to actually, I learned a lot about these floats in the Seatrec webpage, and you have to be as accurate as possible in the modeling of the 3D adventure model. And here is the what I use. That I also, this is a part of a paper I'm finishing about pelagic sargassum, and this is the validation metric I use for the cumulative Lagrangian separation. I run a rolling hindcast around the full mission record. I test with the 7-day time windows and also with the 15 days time windows. And I score everything using the Liu and Weisberg skill score. The formula is shown here. And in the what it measures is the cumulative Lagrangian separation. If you get a skill score near to 1, it's close to a perfect match, and values more than 0.65 are considered skillful predictions. So in the numerator, you can get it's the mean separation distance, and in the denominator is the root mean square spread of the observed track around its own centroid. What are you doing here is like comparing the known flow positions when you run the hindcast against the prediction that are you doing, and what are you trying to minimize is this cumulative Lagrangian separation. And I use this skill score. I introduced it I use the grid search CV function from the scikit-learn library. It's a library is mostly used for machine learning, but it has this function that you can select an output that you want to minimize. In this case, it's the cumulative Lagrangian separation, and you tune the knobs. In this case, I ran 2-phase parameter grid search with 28 combinations, and I test different drift factors because I consider that maybe the float slips in the water in the current, and I also test different time windows. And the winning configuration here, you can see that it was 7-day windows. Even the prediction was 9 days. This was the closest one with a drift factor. These were the main parameters I tuned in the grid search. Drift factor of 0.75. And the big physical takeaway here is that it's important to get a time window as close as the prediction you want to do, and also shortening this time window stops the trajectory errors to growth in time. Here I show you the gap. The main result was the gap was the dye profile, because as you seeing here, the ocean parcels framework with the constant depth, it was the one that got a lower skill score. And as you increase, when you tune, including the dye profile and the right time window and the drift coefficient, it was getting better until we reached the optimal combination, that it was the OpenDrift with the model dye profile, 7 days rainit time window with a current coefficient of 0.75, as I mentioned before. It gave us an overall skill score, a mean score for the whole trajectory of the float since its deployment in the Gulf of Mexico of 0.90, around 0.96, so very close to 1. That is the optimal score that you can get. And here I'm showing you two things that did not help. For example, for the Sargassum drift model that I'm developing, I'm using machine learning velocity correction, but I with the in situ drifter data that I have many more data points, and I have a lot of data that I don't have here with the only one trajectory of the float. Maybe if I can have the whole the trajectories of more of the Seatrec floats, I can do this kind of velocity correction, and I cannot apply here after some tests because it was I realized that it was getting biased result from overfitting. And also, as I mentioned before, I tried to include the Stokes drift in the surface to see if the waves make any impact on the trajectory, but the float spent only less than I think less time in the surface, so it didn't add any improvement to the simulations. In this case, the skill score. And here is the
Jose, this is fantastic. Could we wrap this up in the next 3 minutes? Is that possible?
Yeah, I'm just finishing.
Okay, perfect. Thank you.
The final forecast, the submission I did, it had an error of around 52 kilometers away from the place that the float surface. And here you can see the animation of that summarize the submersion setup. And here is the same animation with the current fields. Here I am showing the deepest layer, the one that I mentioned that is 902 meters depth. This is between June 27 and July 5. This is the 9 days time window. The lessons I learned from this exercise. The first one is that the vertical dive cycle is very important, not just the horizontal drift. So sampling the currents at the float through depth is very important. The second one, use short reinitialization windows to prevent the error growth. And the third one, it was on relied trustworthy metrics like the Lewis-Weisberg skill score, so you can trust the results you are getting from the simulations. Here is the most complete 284 days trajectory before after the finishing the contest. And I want to thank Seatrec for organizing this challenge. And I'm now happy to hand to Knut Frode Dagestad, the winner of the second part of the contest. I look forward for the question during the Q&A section.
Thanks, Jose Manuel. That's great.
Yeah.
So Knut, you're on. Oh, we're not able to hear you.
Can you hear me now?
I can hear you now, yes.
Yes. And now maybe you can see my presentation.
That too. It's all coming in.
Yeah, so thank you for the nice introductions and nice presentations. So we are from the Norwegian Met Institute, so we do drift modeling is one of our many tasks as a National Weather Institute or Oceanographic Institute as well. So I did this alone, but I normally do it with Sean Rabot, who is with us today. He will comment on the machine learning part later, and Gaute Hope as well. So actually, I discovered this LinkedIn post by Jose this summer by chance on LinkedIn. I didn't know about the first round, but I found this post, I think it was just 2 or 3 days before the deadline of the second round. And I found it very interesting because, yeah, it's a very nice type of challenge. Because 5 years ago, DARPA arranged a similar contest in 2021. And Gaute and Sean and myself, we did participate back then. And we had great fun, and we learned really a lot, both from doing the predictions, but also a lot from the similar webinar as we're having now after the competition, where everyone explained the methods, and I think everyone learned a lot. So the last 5 years, we've been hoping for someone to arrange this kind of contest, and now we are very happy to hear that Seatrec did it, and we are even more happy to see that you will continue doing this regularly. I think that's would be very well received by a lot of people, and I think it's probably a lot of people that was not aware of this that would jump in if the word is spread. Yeah, so as I said, this was just 2 days before the deadline. It was in the summer holiday in Norway. So normally I would do the machine learning with Sean, but he was on vacation, so I didn't contact him. He's very enthusiastic, so he would probably have done it, but I was thinking of his wife. Maybe she would not be too happy if he pulled up the laptop in vacation. So I tried to do it on my own on the physical basis. Yeah, so the first thing I did, as I said in the interview with Marta, I did it embarrassingly simplistic compared to what Jose did. But anyway, I will explain. So the first thing was to download the historical track. And I didn't find any download button. Maybe there is one, but so that's the only part where I used AI in this. I was asking the agent to download the data for me. And it found some hidden link. I don't know if it's really hidden, but there was a link there with a historical track of these some 100 days. So I did download that with Python, and then a little commercial here. I ingested it into the X-ray data set to be used with Trajan, which is a Python trajectory analysis package. So this is functionality that was originally, some time ago, it was inside OpenDrift for analysis of the simulations and comparing with drifters. But we realized that this is actually independent of our drift model. This can be used with any drift model. So we separated it as a standalone package for trajectory analysis. So you can use it with any output from any drift model, but also importantly, you can use it with any trajectory data. And even more importantly, if you want to compare our drift model output with observed trajectory. So as you see in the code here, I imported to a X-ray data set with this Trajan package. And then you could do many different things that are specific to trajectories. For example, gridding it to 1 hour time step, as you do here in one line. You could export it to a NetCDF CF compliant format, which is a format that is widely used if you have big data. This was not so big data in this context, so it's okay to have it in a text file. And you can do plotting, and you can do skill scores and many different things. And skill score, for example, is implemented in the Trajan package. And like Jose, we also use this Liu Weisberg skill score. I think it's probably the most widely used metrics to compare to trajectories. So it's not perfect. I think there is no perfect skill score because it has its own characteristics. But I think it's a quite robust one. And I would say it's probably more robust than just using the final distance. But the final distance, I think that's very human understandable, and it's very okay to use that as a metric for a competition. But if you want to improve or optimize your algorithms, as Jose also showed, I think it's better to use this more robust metrics. Yeah, so then after downloading the historical, I was doing some simulation, and the first step is to find an ocean model. And I also just started going to Copernicus first, looking to the Mercator model. And it's many variants of that, but the most high time resolution is surface data set. So I found a 6-hour data set, which is the first one that has depth data. So 6 hours, normally I would like 1 hour, but 6 hours I think it's quite okay with this kind of, on this scale, because it's a quite smooth transition. So it's more important that it goes down to the depth of the monk. So I use this one, and this is the Python script to just trying to reproduce the observed track that was downloaded. And you see here the line by line is very simple. So you just open the downloaded track. And the second line here, I don't know if you see my mouse pointer, but yeah, so I did select only the part out of the Mexican Gulf. I don't know if that's important, because normally you would like to have as much data as possible, but I was thinking maybe the characteristics of the currents are different, and outside the Mexican Gulf would be more representative of, but I'm not sure if that was important, but that's what I did. And then I was gridding into hourly, now daily data. And then I was initiating a simulation where I seed elements along this one element per day along the track. I was here adding this Copernicus data set. So it's very simple. You don't need to download the data. You can just paste this link and it will be streamed during your simulation. Letting the particles live for 24 hours, seeding one element at each day along the track, and then simulating and saving it to a netcdf file and plotting our plot. And the plot looks like this. So the red is the observed trajectory, and the small worms coming out of it, that's the simulated one-day tracks. So I can remove the track. So here you see the green is the observed positions, and the red, it's the end point of the 24-hour simulation. So ideally, they should align, and the red dot should hit the next green dot, because that's the one day later along the real trajectory. And at first I tested with the surface current. I didn't expect it to be too good, because I had read that the monk goes down to 1,000 meter, but just as the first test. So it was a little bit like expected. And then in the second round, the only change, as you see, I put it at 700 meter depth. And this was just eyeballing. I saw a dive figure. I didn't find it again now, so I don't know where it is, but I saw some, and I think Jose calculated it to, was, yeah, 900 or something. So my eyeballing was like 700 meters as a weighted mean depth. Yeah, so as I said, it's extremely primitive. I would have liked to do this kind of dive that Jose did, but I didn't find any information about this time interval. I could probably have searched better, but I was a little bit short of time, so I just tried with this one. And this is what you get, and you see already that it's much better. In the beginning here, it's almost perfect. And then there are periods which is not so good, and then again, it's quite good. So when I saw this, I was thinking that, well, I made a lot of these figures before, and I was thinking it's maybe hard to get something better than this. So instead of investing a lot of time to do something fancy, I was thinking maybe I just buy a ticket in the lottery, because as Paul explained, the arrows will explode anyway. Even if you do something perfect, the arrows will haunt you. So yeah, so I was a bit lazy and just thinking this, maybe I'll try with this lottery ticket. Yeah, so that's all actually. So this the script.
Being lucky can be your strategy. Just to clarify.
Yeah, it won't work each time, but maybe I'm out of luck now. But next time we will try to do something more sophisticated, because I think it's a little bit like playing poker. In a single game, anyone can win, but in the end, the winner will be the one with the best strategy. So we hope to do something more robust for later. So this is the script that produced the winning prediction. So it was not very good, but I think it was not so many participants in the second round. So then it's even easier to be lucky. Yeah, so since we have some more time, I think we can say something about what we could have done. Yeah, so as mentioned, I would like to do what Jose did. It makes total sense, of course, that you include the dives so that you sample the currents at the right depths. But since I didn't know neither the period or the time at depth or at surface, I didn't do it that way. But if I did, I would have included the wind drift when at surface. But as Jose also said, I didn't know that it was only 2% of the time at the surface. And then maybe I agree. Then maybe you don't need to have the wind either, like he found it, that you don't need the Stokes drift because it's so little time. But what I think would be important is the machine learning correction that Sean in a minute can say something about. And so this is, I have some slides for some of this, but this is just an overview. And what we also have done, which is also partly what's done by the machine learning, is that we would fuse, now I used just one ocean model, but I would like to have used more ocean models, like the HICOM or the Oscar and whatever you can find, to combine them all. The more data you have, the better. You just need to weight them differently. The more weight to the better model. And it was interesting to see José's work with the current drift factor. And it was very interesting to hear the interpretation, because my intuition is that since the acceleration is slow, I was thinking that the monk would follow the currents. So my motivation to use the current drift factor would be to compensate for a bias in the ocean model. So if the ocean currents are too strong, I would use a smaller wind drift factor. But that's an interesting topic. That maybe you're right. Maybe it is slipping. But in an area, whether it's slipping or not, anyway, it is a meaningful parameter to tune. And not at least using ensemble models, which we have done quite a bit, is also very useful. Just one slide about the surface. So if it was at the surface, you would need not the current drift factor, but with the wind drift factor, which is normally 0.03 for objects floating equal in the air and in the water. But from this picture, it seems like it's floating almost nothing in the air. So I would guess from this picture something like 1%, which would be then mainly the Stokes drift, since there's no direct windage. But this you can calculate. Some people have tried or have done that, but unfortunately, in practice, I think the ugly tuning would always win over the beautiful mathematics. But it's nice to have some theoretical foundation for what you're doing. But I think tuning, that's what you would like to do in the end. Yeah, so then if Sean has some microphone, he can comment on the.
Can you hear me?
Yes, Sean, we can.
Perfect, yeah. So one of the things we could have done is to try to apply some of the machine learning thinking that we have had in other cases. We just have a preprint on ResearchGate out about what we learned during the DARPA competition. Largely, we learned from some competitors and also from things we found. So you can find all the detail if you Google the title, or you can send me an email and I will send you the full link. If you want to show the next slide. So basically, this is just looking more at the DARPA challenge in not the same data set, but a data set that is very similar. So it's some SOFAR spotter surface buoys, and we only consider hindcast for simplicity, but this could be extended to forecast with a bit more refinement. And basically what we learned during the DARPA challenge is that the things that beat everything else is to do some simple data fusion between different models, especially when different models or products have different main sources of errors. In particular, you know, there are some products that are mostly satellite measurements, and there are some products that are mostly model, and there are some products that are a mix of the two, especially for the surface current. So what we show in this paper basically is that if we take a number of, we can take a number of models for both the wind and the surface water velocity, both based on satellites and model and satellites. If you go to the next slide. And oops, okay, yeah. So what we do basically is that we just build some simple machine learning model, trying both a linear regression, so purely a linear model, and a simple neural network, because this is in theory something that can do any kind of nonlinear combination of all these inputs, and try to predict the one-step advection for 1 hour. And in this specific case, what we show, and this is similar to the finding during the DARPA challenge, is that actually the linear regression gets as good result as the neural network, which means in practice that the neural network, even if it could learn an arbitrary nonlinear relation, it just learns a linear relation in this case. In a sense, it says that the people who developed the model and the satellite products did a good work, because there may be some absolute bias, there may be some things that are, of course, model and measurement issues, but it's mostly just an offset or a constant ratio. It's not a complicated nonlinear issue. So, and the other thing you can see, it's a bit difficult to see maybe on this picture, but this is Taylor plots on the left, it's on the training data set. On the right, it is on the validation data set. And you can see if you use only ERA 5, you get a model that is quite bad. If you use only Oscar, you get a model that's a lot better. Then if you use Mercator CMS Wind, you have both a model for the ocean and for the wind, and you get something that's better. If you use Globe Current, which is a good satellite product, you get something that's really good. But the real best cross is this blue cost, and it is combining all those inputs. So the blue basically combines the data from all the other ones, and it's significantly better than any other linear regression taking alone. If you show the next slide. So what this means, it should not be surprising actually, because if you accept the idea that the product based on satellites and the product based on numerical models are fundamentally different sources of errors, then the fundamental and simplest fundamental theorem of data assimilation says that you can make a best linear unbiased estimator by weighting these together, and you will get something better than any predictor taken alone. So that's exactly what we show, and basically compared to the OpenDrift standard untuned baseline, we get up to 40% better Liu Weisberg metrics on a 2 days perspective. So yeah, this is just the basic best linear unbiased estimator, and this is not unusual. We have another paper where we did something very similar a while ago for a completely different project, basically trying to predict solar irradiance, and we found something generally relatively similar. In the solar irradiance case, the neural network was slightly beating the linear regression, but if you linearize the neural network, you find that it's very, very close to the linear regression. So the gain is here, but is small. Here, in this case of drift, we didn't see any gain. And of course, we did this for the simplest possible set of moving parts so that we could have a very simple proof of concept, but you could do it with varying time coefficient in time to take into account not just hindcast, but also forecast mode, which is what the winning entry during the DARPA challenge was doing. Next. Yes, that was what I had.
We spent our time, but I think this is if there's time for this last slide. I think that could be
please
of interest.
Continue.
Yeah, okay, then very quickly. So ensemble modeling is can be used for many different things. It's really useful. It's of course it's heavy. It's to run ensemble ocean model is a heavy stuff, but it pays off. So this is a paper. It's a graphical abstract from a paper that we submitted this week actually from a colleague. So if you look at the figure A to the left, so it's exactly what we're having here. You have an observed trajectory, and from the last observation, you can make a forecast. In this case, we see the gray lines. These are using each of the ensemble ocean model members. And initially, you don't know which one is the best one from these, and so you just would take the mean or other methods. But if you look at the second last position, and then you can find out which of these members were best in the second last prediction. And then you could assume the best member from yesterday, maybe it also would be the best member from tomorrow. I think it's probably fairly intuitive that it could be like this, but it should be investigated. And that's what we did. So what she found, or we found, is that the best model is indeed, or the best member from yesterday is indeed the best member for the next 1 to 2 days. So so that's the memory of an ensemble. So it's not a very long memory, but I think that's already very useful because when simulating a 10-day trajectory, the first day would be the most important, because if you're getting a bad start, you're already bad off for the next. So I think this is useful. And what you also found is that what's more longer memory is for the bad members. If some members are bad, they will remain bad for a much longer time, 7 to 10 days. So it's more important to blacklist the bad members than to highlight the good members. But anyway, you should here find some weighting probably that you can use the ensemble to a best possible way. So yeah, so I guess this was the last slide from us.
That's great. Thank you so much.
Fantastic. Thanks, everyone.
Wow.
I learned a lot. Okay. Well, so if Marta, can we keep going? Can we? Is that okay? And
I can
we
keep
certainly
going.
understand that we're
So-
going over time. If people need to jump off, that's fine. But I'd like to open it up for discussion.
And you can just unmute yourself and talk.
Can I ask a question now? Yeah. Thanks everybody. This was very fascinating. I learned about this today, so I'm just kind of trying to get an idea of this. But one thing that I was wondering during the 3 presentations is about this idea of the eta term that was introduced by Paul at the very beginning, which is that error that has to do with the physics and interpolations and all those things. And kind of makes sense seeing the last part of the presentations related to machine learning, how taking an ensemble when you're trying to predict the position at the surface, it makes sense to me to work with these ensembles, because the ocean is in contact with the atmosphere, which makes the near surface variability very stochastic in a way. But for the profiler problem, my understanding was that most of the time the profiler stays at 900 meters. So I was wondering if some of you have an idea of how stochastic are the deep currents compared to the surface. I mean, at the surface, we know we can have submesoscale variability and all those things that can at least. By the way, I work with ROMs, so we have the capability of putting drifters in ROMs, and we see this huge divergence. If you have a small error in the initial position of the drifter, sometimes you can see this huge divergence near the surface. But I was wondering how the situation changed when we're talking about the dispersion in the deep ocean. And I don't know if any of you have any experience regarding that, how dispersive, how stochastic are the currents at say 500 meters or 1,000 meters.
Okay, well, let's let our two speakers talk, and I also am happy to get the last word because I love to do that. Jose or Knut, do you have any thoughts?
I think that the water mass at that depth is more homogeneous, like the temperature gradient and is more like homogeneous, and I think that the stochastic factor, it will be less than in the surface. At least that's my. For example, the temperature gradient at that depth is more like a continuous, and I will guess that that a chaotic kind of behavior also in the near to the surface, the mixed layer are more influenced by the winds, and yeah, that would be my response.
E, do you have any comments about the floats, time at depth, etc.?
Yeah, thank you, everybody. Thanks, Javier, for that great question. One thing we can do better next time is to provide more information, how much time we stay at the surface for each dive, how much time we park at the different parking depths. And then, of course, the floats spend most of the time moving up and down, ascending and descending. So we try to park as minimum time as possible at the parking depth. Sometimes we park at different depths because the float is looking for colder temperatures to harvest energy. So that data exists. So we didn't do a good job to provide that information to you. It's hidden in the website somewhere. If you click them, you can find those information. And we try to minimize the surface time. So so the float prediction have a characteristic of both of the surface drifting, parking depths, and then the integrated velocity through the water column. So it's a good combination, all these factors you guys have been talking about. So we learn a lot. Thank you so much. And then next time we'll provide more information, make your prediction easier instead of asking AI to harvest the data from our website. Thank you again.
So Javier, also kind of zooming in on your question a little bit, I think that you were asking about the stochasticity of deep currents. I think that there's kind of a philosophical distinction between are we working in a deterministic regime or are we working in a stochastic regime? And it's a little bit of a moot point. It's like what do we see in the data? And so what I would point you to is there was an experiment called the DIMES experiment where they deployed acoustically tracked floats off in the ACC, and they were very interested in diapicnal diffusivity, and they resolved the trajectories of those floats with acoustically, and they got all the trajectories, and then they did a lot of really great research on looking at the dispersion of these floats, and so you do see a lot of dispersion at depth, and you see a lot of dispersion also in the trajectories of Argo floats, which spend a significant amount of time at depth, and so it's not. But is it stochastic? Is it, it's not. It's you can model it that way, and it kind of makes sense to think about it that way. But I think that another way to phrase that would be there's just variability in the current structure at 1,000 meters.
Yeah, sorry, I that's what I meant. Yeah, variability. No, it doesn't have to be stochastic in a way. Could you mention again the experiment that you referred to?
Absolutely, it's called the DIMES experiment. I'll put a link in the chat. It's a super cool experiment where they put I think like maybe 200 floats. They just chucked them off a boat in the ACC, and they acoustically tracked them, and they saw where they went. And and they looked at all basically they were exploring the question that you were trying to answer the question that you were asking.
All right, thank you.
And for the presenters, if you wouldn't mind emailing me your presentations, and we'll have this link as well to this experiment, Javier. And we plan to create a blog post this week that will have a link to the video, a transcript, as well as the presentations. And so we definitely would like to share that if it's okay with everybody. We'll have that up. I will email the attendees here a link to the blog post, and we'll post it on LinkedIn as well. Other questions? Don't be shy. We have the experts here.
Well, maybe please go.
Sebastian, please.
No, Sebastian, you go ahead.
Yeah, so maybe it's less a question than a suggestion. I was wondering if it is possible to mix the usual Lagrangian approach with how to correct part of the error provided by the usual Lagrangian approach with the Lagrangian coherent structures, as we know that this mathematical tool can help to identify attractors, and that's an idea I've got in mind for the last 2 years.
Did we lose sound?
I think we still have sound. Can you hear?
I can hear,
Paul,
yes.
Paul, we can still hear.
Oh, okay, sorry. I cut out for me.
Did you have a response to Sebastian's suggestion?
No, I'm sorry. It cut out from. Could you repeat that, Sebastian? I apologize.
So I was wondering if someone already think at a strategy to try to merge together the usual Lagrangian trajectory approach with a Lagrangian coherent structures in order to try to correct when the Lagrangian structure tells, oh, you should be in an attractor region to correct the trajectory. That's something I would like to test for the last 2 years, but unfortunately, I had no time yet.
Mm.
So it's another way to visualize data fusion, maybe.
Oh, interesting.
I know that I haven't done that. I've always been fascinated by Lagrangian coherent structures whenever I see papers about them, and it's not something that I know that much about. But maybe Jose or Knut has thoughts.
Yeah, I've done it a little bit earlier and testing it, but I have to say I lost a little bit of the interest because, I mean, you calculate the Lagrangian coherent structures by performing drift simulations, but I don't see that it adds more than you do by just doing your drift simulations in the first place directly. So, but I might have missed some of the points with the coherent structures. But I have some colleagues that are very enthusiastic about them. So.
Do we have any suggestions or comments? If we have no more questions.
I have a question for the two speakers. If you were to identify the lowest hanging fruit next step thing to improve your prediction, what would that be? And you know, outside of the presentation that you know, I know you like you have very distinct ideas that were articulated in the presentation, but outside of the presentation, after you implemented those things, what would be sort of like the next step, lowest hanging thing to improve?
At least for me, like Dr. Chao mentioned before, like having the real like a track of the float in the water column, like because for example I guess that the spend most of the time in the parking at the deepest layer, but apparently spend most of the time in the profiling. And that will be very, very useful for the like getting more details about the about that.
That will be provided. Grant's our guy for that. And any comments or suggestions for themes for future webinars?
Sorry, Marta, you were mentioning before that maybe in the future contests you will be using another float from the infinity.
Yeah, we might be showcasing a different location, is in all likelihood. So we're working on the next contest. We wanted to get the right cadence. At first it was, let's do it every week. And then I think that's too much because Knut Frode's luck is only going to run so far. So we want to be able to have people enjoy doing the process, engage with it as much as possible. So we're probably going to do it once a month.
Yeah. And I also want to mention, you know, a big thank you to Seatrec for sponsoring this contest, and that they're ponying up some real swag. You know, it's like we're floating around ideas. You know, so right now it's like you win the contest, you get a T-shirt, but we're floating around ideas. You win the contest twice, you get like a jacket. You win it 3 times, you get a bag.
You know, waterproof like pelagic.
You get like a little cooler to carry your lunch in. And if there's one thing that's going to make your colleagues jealous, it's like if you show up and you've got the winning you know, lunchbox, Seatrec lunchbox. So you know, we're still working on this, we're still developing this. If there's something that really would motivate you guys or would be fun or I mean, ultimately this is all about having, you know, we're trying to learn here, but we want to make this fun. And so if there's any suggestions that you guys have, please let us know.
Definitely. Feel free to reach out to me or Paul. If you don't have his email, we'll make sure you get it. You should all have emails from me because I sent something to you directly. And don't hesitate. We'd love to hear from you. Our goal is to keep the community engaged and, like Paul said, to have fun here and to learn. There's a lot. We don't know much about the ocean fundamentally, and the more we can learn together, I think is beneficial overall. So we're very excited about the opportunity. And thank you for joining our maiden voyage in this monk competition.
Absolutely. And also we'd like to congratulate our winners. And we would also, and finally, we want to wish Jose a very good luck in his defense. We know that he's gonna crush it. So hopefully the next time we have this webinar, we're gonna introduce Dr. Jose.
Yes.
Hopefully. Yeah. Yeah. And another thing that I want to just to finish, that if you publish the trajectory of a different float for the machine learning kind of correction purposes, it will be a plus having more data. So maybe for the new colleague Jan, it can improve its forecast, maybe with more data to train and validate the corrections.
That actually sounds really fun for us to do this on an ongoing basis. So we can try to do some other partnership there, just, I mean, informal, just as I start looking at the data and what else we can learn from it. So that could be a really interesting path to take. And Javier, thank you for joining. We will definitely add you to the list on everything and really excited. So I will let everyone go. We went 22 minutes over, still kept some of the people. So thank you again, Paul. Thank you so much for hosting this and answering the questions, which I would not be able to do. And so we look forward to seeing you at our next webinar.
Thank you.
Bye, everybody. Thank you so much.
Thank you.
Thank you. Bye-bye.